Good morning guys, and welcome back to my YouTube channel. In this video we're going to be going over how to do every reaction ever. And in today's example we're going to be going over when HBr is added to 1,3-butadiene. But before we get into the content, you know the deal. Please make sure to leave a like, comment, save, and or subscribe to this channel if you like my content and want to support more. But enough with the YouTuber stuff. Let's get into the chemistry content. So consider 1,3-butadiene. Step 1 of every reaction ever. We have to look for the nucleophile. So we're looking for atoms with lone pairs, or we're looking for pi bonds. Here we see we have 2 pi bonds. And our other reagent is HBr. Let's go back to the classical example where we have one double bond react with HBr. So consider this structure. So the double bond is going to flick out to in, grab the H. Why is it grabbing the H? Because the H is delta positive. Why is it delta positive? Well, it's because the bromine, which is electronegative, is pulling electrons towards itself, creating a dipole moment where the electrons are pulling towards the bromine, leaving that hydrogen in an electron deficit. So the hydrogen will be electrophilic. That means nucleophilic things will want to attack it because opposites attract. Where the double bond, if we label all the carbons, and this labeling is arbitrary. I'm just labeling the carbons to keep track of which carbon I'm talking about. So here, if I label the carbons 1 to 3, if the double bond flicks out and it attacks the hydrogen from carbon number 1, that would leave carbon number 2 in an electron deficit. Therefore, carbon number 2 will be cationic. But if we go back to the original structure and we say, well, what if the double bond flicked out and grabbed the hydrogen from carbon number 2? Well, this would have left carbon number 1 in an electron deficit, therefore carbon 1 would have been cationic. So why does this reaction proceed where the carbocation is left on carbon number 2? Well, this has to do with the stability of the carbocation. And the trend goes 1' carbocations are much less stable than 2' carbocations, which is much less stable than 3' carbocations. And what I mean by primariness is the amount of alkyl groups, so carbon groups, that are attached to that carbon with the positive charge. Because alkyl groups are like electron gun throwers. So they are electron rich, but they're not electronegative. That means they are not greedy groups, so they are going to donate electrons in the direction of a group that needs help, so a group that is cationic. So when carbon number 2 bears a positive charge, it would be considered 2'. So when carbon 2 is cationic, it has 2 CH3 groups that can throw electrons at it and help it out. So carbon number 2 will be in less of an electron deficit. For example, in comparison to carbon number 1. When carbon number 1 is left cationic, it only has a CH2 group that can throw electrons in its direction. I like to relate this concept to charities. So let's pretend when a carbon is cationic, it is a charity. And alkyl groups are billionaires who like to donate to the charities. If you have 1 billionaire donating to your charity, you're going to be pretty rich. But you're not going to be as rich as the charity that has 2 billionaires donating to its charity. It is going to have a lot more funding than the charity that only has 1 billionaire donating to its fund. Just like a carbocation that has more alkyl groups attached to it is going to be more electron rich. And then the final step of this reaction, where we have an alkene react with HBr, would be that bromine minus that was expelled from the initial nucleophilic attack of the pi bond on the H, a part of HBr, which was 2 in, 2 out, expelling that Br minus. Br minus can come in and attack the carbocation on carbon number 2, 2 in, and then you form your product, where the bromine ends up on the more substituted carbon, a part of that initial double bond. With that said, guys, now it's time. We're getting into the addition of HBr to 1,3-butadiene. So there's 2 pi bonds here. Which one is going to flick out and grab the hydrogen? Now I'm confused. It's the same thing. Step 1, label all your carbons. So on 1,3-butadiene, let's label all the carbons. So carbon number 1, 2, 3, 4. So let's focus in on the double bond between carbon number 1 and carbon number 2. So we've established that double bond could flick out from either of the carbons, a part of that initial double bond. So what if it flicked out from carbon number 1? So then carbon number 2 would become cationic. Okay, well what if that double bond flicked out and grabbed the hydrogen from carbon number 2? Well then carbon number 1 would be left cationic. Which carbocation is more stable? Okay, well in example number 1, we had a 2' carbocation. And in example number 2, we have a 1' carbocation. So yes, the first example wins, where the double bond would flick out and grab the hydrogen from carbon number 1. But that's not the only reason here. We also have resonance stabilization. So we have delocalization of that carbocation. That carbocation can not only be helped by a 2', it can also be helped by the double bond in its vicinity. So we can draw a resonance structure. 2 in. So now how you can think of this is, in example number 1, carbon number 1 would have to bear that positive charge the entire time. Nobody's coming to help it. There's no conjugation. But in this example, carbon number 2 is going to share the positive charge with carbon number 4. So just like the grocery example we went over in my last video, when we went over the formation of a halohydrin. If you haven't watched that video, go back and watch it. If you went grocery shopping with your parents and you guys got home back to your house and your parents asked you to take in all the groceries and you were trying to take it all in one run, and your neighbor ran over and you had 5 grocery bags on each arm and was like, hey, let me help you out, and they grabbed 2 of those grocery bags off of each your arms, then you would carry less of a load. You would be happier. That is the exact same thing that is happening here. So the resonance stabilization, making it so carbon number 2 does not have to bear that positive charge the entire time. It now shares it with carbon number 4. So this structure is stable, unreactive, or less reactive. So then from here, we could say, well, we got a Br minus in the solution that could go and attack 2N because opposites attract, carbon number 2 because it is cationic. And then we get the 1,2 addition product. But now, going back to that intermediate, where the carbocation was on carbon number 2. When we consider the first resonance structure, well, that means the carbocation is also on carbon number 4 50% of the time. So that means that bromine not only sees the structure where the carbocation is on carbon number 2, but it also will see the structure where the carbocation is on carbon number 4. So that bromine group can go 2N and attack the carbocation on carbon number 4, and then we get the 1,4 product. So that is why we get 2 products here. But hold on. Let's do another example that's a little more complicated to see if you guys can still apply this concept. Step 1, we gotta label our carbons. So label them 1, 2, 3, 4. Let's focus in on carbons number 1 and 2. So let's say that pi bond flicks out and grabs the hydrogen. As we've went over, 2 things can happen here. The double bond can flick out and grab the hydrogen at carbon number 1 or carbon number 2. So let's look at those structures. When carbon number 2 is cationic, it is a tertiary carbocation. When carbon number 1 is positively charged, that means it is a 2' carbocation. Which one is more stable? Well, 3' is more stable than 2', which is more stable than 1'. So when the double bond flicks out and grabs the hydrogen from carbon number 1, it leaves a more stable tertiary carbocation. So that pathway would be more favorable. So then we have the bromine floating around in solution where opposites attract. It is anionic because when the double bond initially flicked out and grabbed that hydrogen, it expelled the bromine, 2N, 2L. So that bromine can go, I see you, I'm going to attack you, 2N. So now we get our 1,2 addition product. But now let's go back to that intermediate. Okay, well, this intermediate is also stabilized by resonance. So let's draw the resonance structure. 2N. Now the carbocation is on carbon number 4. So the bromine can also attack the carbon with a positive charge, carbon number 4, 2N. So that would be our 1,4 product. So now we have a problem. Your teacher might also tell you there's a certain temperature that this reaction would happen at. They might throw 50 degrees Celsius at you or 0 degrees Celsius. So let's talk about the effects of temperature. So let's go back to 1,3-butadiene and talk about the effect of temperature. So let's say this reaction happens at 0 degrees Celsius. Well, what happens now? These electrons do not have much time to rearrange. When you are cold, you just want to get in and get out. When you are cold and you got to make it from your house to your car, you're going to sprint, right? You're going to do whatever it takes. You're going to take the shortest path available for you to get from your door to your car. You're not going to walk around the block. You're probably not going to go say hi to your neighbor when it's minus 40 degrees. You're going to run from your door to your car. Whereas when it's 20 degrees Celsius outside, you might stop and smell the flowers, talk to a neighbor, and then go into your car. You're chilling. It's warm outside. You're having fun. When it's cold outside, you're not having fun. You just do exactly what you need to do to get stuff done. So with that said, when the temperature is cold in a reaction, the 1,2 adduct is going to be the major product because this is the first carbocation that is available to the bromine. And the bromine's cold, so it just wants to get the job done. So it sees opposites attract, 2N, you get the 1,2 adduct formed as the major product. We got to remember sometimes that bromine is also going to see carbon number 4 bearing a positive charge. So it's still going to sometimes go attack 2N on carbon number 4 when carbon number 4 is cationic. But that would only be a minor product when the temperature is cold because it takes effort for the electrons to resonate and go 2N and change that cationic charge from carbon number 2 to carbon number 4. And since it takes more time and more effort, it's going to happen less often when the temperature is cold. Okay, well now let's consider the exact same reaction, but let's say the temperature is 60 degrees Celsius. Well now the 1,4 product is going to be the major product because these electrons have time to move around. They have time to smell the flowers. They have time to hang out. So yes, the carbocation is initially going to end up on carbon number 2. And the bromine will see it, yes, but those electrons will conjugate. They're going to go, you know what, we got the energy to do this. We got the time. It's warm outside. We're having fun. And it's going to go 2N. And that's also going to leave carbon number 4 with a positive charge. So there's going to be that balancing act. Carbon number 2 is sharing that positive charge with carbon number 4. So the bromine is going to be able to attack carbon number 4 where it is cationic. So the major product when it's warm outside is going to be the 1,4 adduct. Okay, now question is why? Why is the 1,4 adduct a better product? Because clearly that's why it's going to be the major product when the temperature is warm. Is because it's the more favorable product. The answer to this is the substitution at the double bond. So here we can see the 1,2 adduct creates a double bond in the end that is 1'. So it's substituted with alkyl groups in the same fashion as we talk about carbocations 1 time. So it is a 1' double bond. Okay, well, the 1,4 adduct creates a double bond that is 2'. So the same trend occurs. 1' double bond is less stable than 2' double bond, which is less stable than a 3' double bond, which is less stable than a 4' double bond. That is it, that is all. Let's do one more example. Consider this reaction at 0 degrees Celsius. What's going to happen? Okay, label the carbons. 1, 2, 3, 4. The double bond is going to flick out, leave the more stable carbocation behind. So it's going to grab the H, HBr. So now carbon number 2 has a positive charge. And remember, it is cold outside. The bromine is pissed off. It just wants to get exactly what it needs to get done to finish the job. So it's going to go 2 in, attack carbon number 2 that is bearing that positive charge. So the 1,2 adduct is going to be the major product. But the 1,4 adduct will still form, but it's going to form less of the time because it is cold outside. So we're going to have major and minor products. Hope this made sense. Yeah. If you made it this far, thanks for watching this video. I hope this helped. If you have any questions, comments, or concerns, please let me know in the comment box down below. I reply to all the comments. If you have any concerns, I will make another video to try to clear it up. And yeah, make sure to leave a like, comment, save, or subscribe to my channel, please. Please. Let me know what concept you want me to cover next. And if you don't let me know, I'm just going to keep flipping to a random page in my OChem textbook that I got in second year. That's what I've been doing. Flipping to a random page in the OChem textbook and going, sure, I'll do this one today. So if you don't tell me which one you want me to do next, I'm just going to do that again. Have a good day.